Okay, Assalamualaikum and good day. Just to recap a little bit on fugacity, what we have learned or what I have expected you to learn, right? So for fugacity, I shared a lot of existing YouTube videos because I think they can explain in a better way than if I explain myself. So if I just want to recap about fugacity, um, so basically we have learned about fugacity and fugacity coefficient, and we know that it's just another term that will be very, very helpful, especially when we have vapor liquid equilibrium later on. So we came across the definition of fugacity for pure species, and then we look at for mixture, basically more or less the same as in previous item. So we look at the fugacity in mixture and solution. We look at the fugacity in binary or multiple component, right? And then we look at different equation of state, right? So we have different equation of state that we can use. We can also use Lee Kessler and also virial correlation and also a generalized correlation. Basically, what you have learned. Then we look at also the new term, what we call ideal solution model. So we have ideal gas, we also have ideal solution. So if you look at these two, they are basically more or less the same, right? Um, but in ideal gas, we assume that it's just for gas. In ideal solution, it can be gas, liquid, or solid, it can be anything. Um, it's just the denotion is a bit different, okay? And from there, we look at summability relation. So this is also quite important for you to remember. And then the Lewis-Arundel rule. And we look at the excess properties, which is actually basically the same with residual properties. But again, the residual properties um, refers to the ideal gas, and this one refers to the ideal solution. Okay. Um, yeah, and then lastly is this table, which is shows a summary of the equation. Again, you will be using quite a lot on this about from this table. Okay, right. So in here, I give you several examples and also the answer in YouTube, so it's easy for you to understand better. All right. Okay, and also this is your assignment. So we're just going to look at example 11.5. I hope you can do. It's a bit actually. The example is a bit straightforward. Very, very straightforward. If you were to do it, um, I don't think there will be a lot of problem because it's quite easy to be explained, right? So that was 11.5 that I wanted you to try, and then what I'm going to show you is 11.7. Let me just see, where is my 11.7? Just a moment. All right, this is the one. So the question for 11.7 is determine the fugacity coefficient as given by equation 11.63 for nitrogen and methane at N2 and CH4 mixture at 200 K and 30 bar if the mixture contains 40 mole percent of nitrogen. Experimental barrier coefficient data are given. So you are given beta B11, B22, and B12. So it's quite straightforward when you are asked to use equation 11.63, 11.63. Okay. And you can also use the equation 11.63a, 11.63b. So by the definition, if you look at this, um, okay, right. So you look at this. This is given, yeah. This is given. So what we do is basically we just plug it in, and then we solve based from 11.63a and 11.63b, and then you will get the fugacity coefficient, and then uh, put that in equation 11.62, and you will get the compressibility factor. Okay. Right. The next example that I want to show you is example 11.9, in which I feel that, again, for me, these examples are very straightforward. Where it says that use estimated the coefficient for equimolar mixture of methyl ethyl ketone and toluene. So number one refers to the first species, two refers to the second species, okay, and then set all as 0. So we take from equation 11.70 to 11.74 from page 409. Okay, so you are given this data. So this is quite clear. When you want to use this data, means that when you are given this data, means we have to use the EOS. All right. Okay. So you calculate everything together. All right, and then you can calculate based from equation 3.65, 3.66, and 11.69, and you will get your B11, B12, B2, B21, sorry, B22. Okay, so once you have finished that, okay, you can do the calculation. I did not take the picture for page 411, but basically you just plug it in again from equation 6.363a and 11.63a and 11.63b, and you will get the answer, the coefficient for both. All right. So basically, what it tells you is that when we use generalized coefficient, okay, depending on the information that we have, okay, if you were to, for example, in question in exam, for example, you look at what informations are given, and then you can select which equation that you want to use. Okay. Okay, and this is we go to excess properties. As I mentioned to you, excess properties is just like residual properties, but it is in solution. So if you remember in my previous slide that I showed you the table just now, this table, yeah, this is the table, which is very, very important for lots of things. All right, so we play around with whatever that we have. Again, it's all about what information you have and what equation you need to use based on what is given. Okay, so for 11.10, it says that if CP, okay, for the excess property is constant, independent of T, find the expression of all the G, S, and H. And these are all given, the correlation are given in the table. Okay, so and you are given, let's say it's a constant, because we know that it does not change. So from the table, we know that P for excess property is this, okay? And then simply just bring the t here back to here, and you will get this. So what you have to do is basically integrate both of double integration, okay, second integration, so you will get this in, and then nc is another constant, so you have constant a, constant b, and constant c. All right. And since you know that h is equal to g plus ts, so you combine a and b and you get this equation, you get c equation. Okay, so basically this is the general equation, derivation of the general equation, or the general expression. And then it says that, okay, from this, the one that you have developed, find these values given that for benzene and hexane at 50 degrees C, given the properties at 25 degrees C. So this is the initial properties, right? Or HB naught. Okay, so, and we know that Cp is constant, all right, independent of T. So whatever the temperature is, even if the temperature increases, it doesn't change. And you have A is equal to this, which is given right here, 2.86 joule per mole. Okay. Um, right. And then, okay, this is actually, there's a typo here. It says from equation A and C, but actually it's actually from equation C. From equation C, H is equal to AT plus C. So you will get C is equal to H minus AT. So this is actually from equation C, and H is given. We use this at initial value, which is T naught. So H naught is 897.9. Okay, and then you get your A and you get your T, so you get your C is this. And from A, you get your B, your constant B, given your G. Okay, and then you substitute, and then you will be able to solve, right? um so basically, uh these are the examples about this topic. Again, you have to remember, what we want is the same thing over and over again. We want to get our H, S, G, similarly previously, in your solution thermodynamics, in terms of pure substance. So those are the things that we have been calculating. So basically, so far you have learned to calculate or to derive the equation for all these thermodynamic properties, given whether it's gas, it's pure, it's ideal gas or ideal solution or a mixture, and so on and so forth, right? So the next chapter, we will look at vapor liquid equilibrium. Okay, um, and we will use the information or the knowledge that we have learned so far, and apply it to that. All right, so thank you so much.